Brain Weaseler, you're off the hook now because I have the holy grail of a Flex Master. Hi everyone! Today I'm going to tell you a story about how I was duped by Frank Hogg Labs and their trickery and shenanigans and all of the copying and repairing and modifying over the years. Because it turns out that the disk I was holding up on the CoCo Nation is actually a master disk, but I didn't figure it out until I was trying to record this video. So, let's get into it. So, where did I start going wrong when I started this project? Well, originally, before I started this, there was a copy of Flex that was on the Color Computer Archive. I've talked about this before. It's actually this zip file right here. It contains what was available before I did this project. And so I figured out, of course, that what's contained in the zip file is not actually directly usable. It needed some conversion in order to get it to a usable state. So I did that conversion. I converted the disk image to DMK and SDF. After I had completed the conversions and had working disk images, it was time to figure out how to use it. So I went to the manual, which is this Frank Hogg Laboratory Color Flex. And this actually contains a tutorial. So I started to follow the tutorial and found something didn't work. Let's go through that. Alright, so I have the tutorial open here on the left, and I have XOR open here on the right, and I just started going through it. Yeah, the first page, you put the disk in the drive, and basically, what do you do with it? You type run flex, fine, run flex. This is going to take a few seconds to boot up. There we go. Type the date wrong as usual. Today should be the 11th. All right, we entered the date. And on the next page of the tutorial, we should see, nice, huh? See if that actually works. And there it is. And +++ means that Flex is up. And we can just do a disk catalog. Yada yada, how nice. You have just commanded Flex to give you the catalog of all the files that reside on disk drive 0. Great. Very good. Now you have used Flex. Okay, so the next thing that they have here in the tutorial is, now that you're just about a pro, the next thing you'll probably want to do is make a backup copy of your Flex disk. So those are the instructions that follow. And it very clearly says there are 5 steps to this procedure. Just 5 steps. All right, we're going to go through those right now. So the first step is we prepare a new disk. And they basically say to run new disk. I want to make a comment here that Color Flex actually has 2 versions of new disk, as shown here. The difference between them is the disk formatting. As you may be aware, a standard color computer disk has 18 sectors per track, and that's what's produced by new disk A. New disk command was an earlier version of new disk that only puts 17 sectors per track, so it contains a little bit less data. Instead of using new disk as they show, we're going to use new disk A. And we just go ahead and run that. Are you sure? Yes. Scratch the disk in drive 0, and the instructions say before you go on, you need to insert a disk into the drive. So this is off screen. You can't see this, but I told XOR to create a new disk image and calling it test.dmk. It is important that you use the DMK format. Otherwise, the special flex formatting will not be saved on the disk. So with test.dmk in the drive, I can now continue. Yes. Now we have to enter a bunch of parameters. Double-sided disk, I want to save a little bit of time, so I'm going to say no. Double density disk, yes, it has to be double density. Number of tracks, I'm just going to put a standard 35 here. After number of tracks, then I enter the volume name. Volume name, be original. All right, we're just going to call it test. Volume number, we'll pick a good round number here. And now it's off in formatting. We'll come back when this is finished. Okay, the formatting is complete. Now it's time to return to the tutorial. We're on step 2. The next step is to use PUT on your newly formatted disk. And here's what the procedure will look like. So we put the flex disk back in the drive. And we run PUTBOOT.LDR 0. Not found. What? Yeah, so I was trying to follow the tutorial and it's not here. So I was a little confused what's going on. So now we begin the deep dive portion of this video. And yes, it's going to be technical content.
Warning, technical content ahead.
Here we go with the deep dive. Not a master disk, wait a minute. Oh yeah. It's a master disk. So the first thing we're going to go through is a little bit of background information so that you can understand what I look at later and what it all means. Okay, so I've shown this slide previously, but this is what the layout of a flex disk looks like. And this is straight up the technical system consultant's specification for how flex disks work. Track 0 has 10 sectors, is single density. The remainder of the disk can be either single density or double density. And in the case of most of the later flex systems, including color flex, you have 35 to 40 tracks, 18 sectors per track, can be double-sided, but this is what the TSC specification looks like. So showing this another way, track 0 256 bytes per sector, 10 sectors per track, single density. And the remainder of the tracks, as we said, are standard double density tracks with 18 sectors per track. 35 tracks, 40 tracks, fine. Has to be double density, could be single-sided or double-sided. In this case, we're talking about a single-sided double density disk. So it has 159 kilobytes of data available on it. So we're going to go even deeper. We're going to talk about the content that is on track 0. So on the top, I have all 10 sectors, and I have described what these 10 sectors actually do. So if you look at sector 1, it happens to be grayed out in this case. It's not used for color flex, but most other flex systems, sector 1 and possibly sector 2, contain what's called an IPL, which is an initial program loader. But in color flex, we don't use that one. So sector 1 is blank, sector 2 is blank. Sector 3 is what's called a system information record. We will look at that in detail in a moment. Sector 4 is blank, and the remaining sectors 5 through 10 contain directory entries. So let's look deeper into the system information record. The system information record contains the volume name, volume number, the first track and last track. Those entries are about the free space on the disk, has a count of the number of free sectors, the date that the disk was created, and one important thing that we're going to look at when we get into the nitty-gritty details farther is the high track and the high sector. The master disk has something very interesting there, which I will show. Next up, we have detail on the directory sector. So the directory sector, the first 2 bytes are a link. I'll explain how the link works in a minute, but basically it's the next track and the next sector, and it forms a chain of sectors. So the next 14 bytes are zeros, and then we have a 24-byte directory entry. 8 bytes for the file name, 3 bytes for the extension. These are null padded. So that means that if you have a short name, shorter than 8 bytes, the remainder will be nulls. Usually extensions are 3 bytes, but you could not have an extension as well. You have attributes, you have the start track and the start sector of the file, you have the end track and the end sector of the file, you have the size of the file in sectors. Map type basically says what kind of file it is, and you have the creation date. Each of the 6 directory sectors contains 10 entries. So this disk, if it's single-sided, you can have up to 60 files on a disk. If you have double-sided, then you can have more. You just have the next track and next sector, just keep pointing to more directory sectors. It can be extended past what you actually get on new disk. The FLEX code actually doesn't really care. But this is what a directory sector looks like. The next thing we're going to look at is we're going to look at what a data record, data sector, actually looks like in FLEX. Every sector that contains data, including the directory, the first 4 bytes are reserved. And it has what's called a link. And the link points to the next track and the next sector of the file. And there's also typically a sequence number, which basically allows you to know whether you're on the first, second, third, fourth, etc. sector of the file. If there are no more sectors following, the next track and next sector will be 0. Okay, so after the 4-byte header, you have 252 bytes of data. And here's a little example of a file which has 4 sectors. And here we're showing how the links actually work. So as we say here, the file starts on track 1, sector 1. And the first sector points to sector 2. Sector 2 points to Sector 3. Sector 3 points to Sector 4. And then Sector 4, we have a next track and next sector is 0. So that's the end of the file. This is how files actually work in FLEX. They're actually linked through the link bytes, the next track and next sector at the very beginning of the file. Okay, so this is all of the technical background that you need to have to understand what happened next in my story. All right, so we showed all the technical details. Now we're actually going to look at a live disk image. So I have a little utility program that I wrote. Flex, CoCo, tools, disk tool. And we actually are going to look at the master disk, which we were using for the demo just a moment ago. This allows us to inspect tracks and sectors and get more information about it. So let's just look at the system information record. And we don't actually have to look at the bits and bytes here. I have a utility which helps us decode this. All right, so we've decoded everything in the system information record, the volume name, the volume number. It says 502, but this is actually version 503. That's great. Yeah, we have November 27th, 1982. But what's actually really, really interesting to note here is we know that color computer disks by stock have 35 tracks. So this track number is 0 based. This is telling us that actually the flex portion of this disk has 34 tracks. This was very confusing when I was doing the restoration. But okie dokie. So system information record says we have 34 tracks. But that's not actually the case. So we can look at the directory sectors, which I said started on sector 5. Here's a directory of sector 5. If I type this right, here's 6. 7. Now, when we get to sector 8, there's something weird here. It looks like somebody deleted this file, PUTBOOT. If you notice up here, PUTBOOT is on this line here, and it goes up to here, 24 bytes. But the first one is FF. Somebody has deleted this file. Okay, we actually need that in order to create a new master disk. Why did somebody delete it? Well, if we look at the directory entry, it's a little bit strange. It says the start track is 21, the start sector is 5, the end track is 21, the end track is 5, and the size is 5 sectors. This doesn't look right. Okay, the file was deleted, but nothing stops us from actually looking at track 21, sector 5. Oh, it looks like there's actually some code here. Huh. I wonder why it doesn't work. I got to this point, I figured out there's some code here, but it does not seem to be working. Somebody deleted the file that I actually need. So this is what I meant. At least this disk that came from the Color Computer Archive, this one can't really be a master because somebody deleted one of the programs that we need. I guess that's it for this disk image. Bootloader was deleted. It seems like a really strange file. It doesn't work. So I thought, well, dang it. Guess that means that this one isn't the master, and I went on the hunt. I had remembered in the back of my memory somewhere, somebody gave me a bunch of color computer stuff. I think it was about 20 years ago. And I had forgotten that there were some FLEX stuff there, and that I actually had a physical disk. So I have a grease weasel. I went and retrieved the disks that were actually still in my parents' house, and I got out a drive and I got out my grease weasel and I made an image of the disk. And I didn't really study it that much, but I guess I just assumed that this one wasn't a master either. But to be honest, I had never tried the tutorial procedure with this particular disk until the other day. I just assumed that this one was not a master as well. Well, let's see how that turns out. So I made an image of that disk and I have it attached to XOR here. And just like before, I type run flex on this. This should be version 5.0.4 because that's what the disk actually had. All right, type the date wrong again. Yeah, today's the 11th, so that should be fine. All right, now I don't need to format the disk again. I just copied the DMK file from the previous demo that we attempted. I just copied that over here, so I have that ready to go. Now, let's continue where we left off, which was step 2, that we need to run PUTBOOT.LDR. And this time we're going to run PUTBOOT.LDR from the 504 master, not the 503, not really a master. All right, so it says put your flex disk in the drive and type PUTBOOT.LDR 0 and hit enter. And then when prompted, put in the disk that you want. Okay, so I'm going to go ahead and do this off screen. I'm going to insert my test.dmk, which is now in the drive. Do we want to put the bootloader? Yes. And this time it seems to work. So I wonder if that means that that disk that I have really is a master. Now that PUTBOOT.LDR actually worked, we can continue the tutorial. So let's go ahead and do that. Okay, so it basically says put your flex disk back in, which I will do now. And then we want to run a command called single disk copy. This was actually written by Dale Puckett, interestingly enough. So do single disk copy, and we're going to copy 0.flex.sys. And we're going to copy this from the master disk, or the purported master disk, to the backup. Okay, enter on this. Enter the source diskette and press enter. We already have the source diskette, so it's going to load that up into memory. And now it's asking for the destination diskette. Again, off screen, I'm going to insert the test.dmk and press enter. Okay, single disk copy complete. So this is actually the boot code has been copied to our new disk. So the next step is we have to run link. And link, what the command does is it actually tells the IPL, the bootloader, the initial program loader, it actually tells it what track and what sector to start loading FLEX from. This is an important step in actually creating a boot disk. All right, so we need to put the FLEX disk back in 504 master and link 0.flex.sys. Okay, and it asks for confirmation. We switch disks back to the test disk and we type Y. Okay, looks like it's done. Continuing in the tutorial, they have you copy a bunch of other stuff to the disk. I'm not going to bother doing this for this demonstration. So we think at this point we actually have a bootable FLEX disk. So what I'm going to do at this moment is I'm going to eject the disk, going to restart XRAR and see if we can get this to work. I think there's a problem here where it may not actually boot up, but we can try it anyway. So the newly created boot disk I've just inserted in the drive. And there we go. Run FLEX and see what happens. Now, when I ran into this before, it did not work the first time. I think there's some kind of, oh, wow. This time, it actually worked. How nice. I shouldn't have said anything. I shouldn't have jinxed it. Well, we don't have any programs on this disk because we didn't copy any. So what this means is that I have successfully followed the tutorial procedure using the master disk, the image of the physical disk that I actually have. I've used that to create a bootable disk. So I think that this means that the disk that I actually have really is a master. And to be honest, I just never tried it. I just thought, well, this one is going to be messed up too. So I was really surprised by this finding, that I was able to successfully follow the tutorial and create a new boot disk from it. So I wanted to figure out how this thing actually works and why it didn't work on the disk that came from the Color Computer archive. So now we're going to go even further down the rat hole and go into even more technical details. So let's go ahead and go straight into that. I'm here in the demo2 directory, which has the master boot disk which we just used, and it has the test.dmk file which we just created. So we can take a look at both of them. using my little tool. Let's bring that up. Okay. The first thing that we're going to look at is let's actually take a look at this master disk to see if it's any different than the one from the Color Computer archive. So, as you see here, the system information record is the same. So this one, instead of saying volume number 502, it says volume number 504, but the number of tracks is actually the same. 34 tracks, 0 to 33. And we'll find out more about that as we get into it. So let's look through the directory sectors. 5, nope. 6, remember we're looking for that PUTBOOT. 7, slow on this one. Okay, here it is. It's got the same weirdness here. It starts on track 21, sector 5, ends on track 21, sector 5, but it's 5 sectors. Okay, weird, very weird. So now, let's take a look at 2105. Yeah, this kind of looks the same as what we had before on the other disk, but we won't know for sure unless we check it out and like disassemble it and whatnot. So I'm actually going to do that. I want to write 2105. Let me write this out to a file. And we're going to call this FAKEPL.BIN. Okay. So yeah, it's 252 bytes. This tool allows us to actually inspect the different sections of a FLEX binary. Okay. So, FLEX binaries have two different kinds of records. They have a data record with an address and a length, and they have a transfer record. So this particular file actually does not seem to have a transfer record, which is strange if this is supposed to be executable code. But let's take a look at it anyway. It looks like the program starts loading at 100, and then there's some more stuff at 13D, some more stuff at 194, but there's some really interesting stuff. Why are we loading something at C880? And why are we loading something at C881? That's kind of a head scratcher, but I actually figured out what's going on here. So I took this and I actually disassembled the code that's contained in the sector. And I had said previously that I actually found source code for this bootloader. So I was actually able to follow the original source code that I had along with my disassembly and actually figure out what was going on. So I have that here. So let's go ahead and read the comments here. Diversionary sector to hide bootloader. This code is to be stored in a special sector on the FHL ColorFlex disk. The bootloader directory entry should point to a sector containing this code. The link field of the sector should point to itself. The sector will contain two binary records, each of which will overwrite 1 byte in the link field in the FCB to change the linkage. These binary records must be changed using examine to point to the first sector of the actual put loader program, which must be stored such that backup will not copy it, and which must auto start. Now, this is kind of a whole mouthful. There's a lot of stuff going on here in this one comment. Let's just start at the top. This code is to be stored in a special sector on the FHL color flex disk. The putloader directory entry should point to a sector containing this code. And yes, we actually did see that when we were in here. There's a directory entry, as we were just talking about, there's a directory entry for PUTBOOT, and it points to the code, which is on 2105. Right? So that's the first part that it's talking about right here. Now let's go back to the second part. Okay, going back to the second part. The link field of the sector should point to itself. Okay, let's go ahead and check this one out. Okay, so they're talking about the link field of the sector should point to itself, which is the first 2 bytes. So we're on track 21, sector 5, and this is the link field, the first 2 bytes. They're pointing to track 21, sector 5, exactly like the comment says. So far, so good. I think we're doing pretty good here. Okay, the sector will contain 2 binary records, each of which will overwrite 1 byte in the link field in the FCB to change the linkage. Ah, interesting. See, in the disassembly, we have it here. We don't have it 2 different records, but basically there's some stuff here. It seems like it's in the System FCB. So let's take a look at that. We already actually saw this a moment ago, but we'll just look at it again. When we ran FLEX.BAS, right? So there's some code, and it said that there are 2 sections which overwrite the link field in the FCB. So we need to go investigate what these 2 things are doing. So this is some code, and this is one of the 2 sections, and this is some more code, and here's the other section. So far, it's exactly like what the code actually says. Okay, we're going to investigate what's going on with this link field thing in just a moment. Let's go back to the comments just to make sure. Okay. These binary records must be changed using examine to point to the first sector of the actual put loader program, which must be stored such that backup will not copy it. Okay, so these binary records point to the actual put loader program. So we can see it here in the disassembly. It's basically telling us that there's something on the disk at this track and this sector. So 22 is going to be 34, and that means track 34 of the disk, sector 3. There's something on track 34 of the disk, sector 3, is what this is telling us. So at this point, we'll come back to what's on the disk at this location. I think I want to explain what's going on with the C880 and what they mean by changing the linkage. So going back to my slides, I already explained that each data sector in the file has the first 4 bytes, which contain linkage information and sequence information, next track and next sector, and there's 252 bytes of data. And I also went through this example of a file which has 4 sectors. There's a little bit more. We talked about the PUTBOOT.LDR directory entry already. We said that it's a little strange. It has the start track is 21, start sector is 5, end track is 21, end sector is 5, and then the actual PUTBOOT.LDR program, the sector, the linkage actually points to itself, which is strange. So this is just showing you what we went over, what we saw on the actual disk. So now let's explain what they actually mean by changing the linkage, overriding the linkage. So I am actually looking at the Advanced Programmer's Guide, and they have a system memory map here. Okay? And what we note here is they have a section at C840 to C97F, which is called a system file control block. The address that we had was C880, so that appears to be 64 bytes into this block of memory. Further up in the manual, they actually explain exactly what's here in the FCB, byte for byte. The file control block. The file control block starts at C840, and then C880 is going to be 64 bytes into this block of memory. So let's go there. All right, interesting, very interesting. So starting at byte 64 is a sector buffer. These bytes contain data contained in the sector being read or written. The first 4 bytes of the sector are used by the system. The remaining 252 bytes are used for data storage. This is exactly what we showed earlier. So this offset here is going to be C880, and it contains the data read in from the sector. Okay, this is starting to make a whole lot of sense now. All right, so we're going to read the comments one more time, and it should make sense. The sector will contain 2 binary records, each of which will overwrite 1 byte in the link field of the FCB to change the linkage. Okay, we know that the first 4 bytes are the linkage information. The first 2 bytes contain the next track and the next sector. So in the FCB, that's going to be right at C880. So we are in fact telling the loader, we're tricking it. We're basically, this is one sector that we're loading in, and the sector contains multiple binary blocks. When those binary, so the operating system reads the sector in first, and while it's reading in the sector, we actually modify the data in the sector to point to a different place in the disk. So when it goes to actually say, hey, what's next? What do I need to load next? It actually goes to a different place on the disk because we overrode it. And the place that we're going on the disk is, again, track 34, sector 3. Okay, very, very interesting. I think we need to go to our disk and then actually look at what's there. So we opened our disk again, and the sector that we looked at again was on 2105. And if we look through this very, very carefully, we said 61 bytes. Unfortunately, this is printed in decimal, but somewhere over here, we see the record. C881, and we have 3 bytes. 1, 2, 3. These 3 bytes. We saw those in the disassembly. Then there's another section that goes on for 128 bytes. So it's going to be over here, A or B, somewhere around here. Here it is, C880 for 1 byte, and we have 22. So yes, it's all here, right in front of us. Well, I know that the system information record says that there are only 34 tracks on this disk, but apparently there's something on this disk at track 34, sector 3. There's something actually here. So this track is actually not part of a FLEX file system at all. But there's the 35th track actually contains some program data. And I think it's 5 sectors long. Yeah, it looks like it's 5 sectors long. So I'm not quite sure what this thing is, or I wasn't when I was first looking at this. So what can I do? Well, I can assemble these 5 sectors into a binary file and then take a look at it. So let's do that. We said 34, 3. Write that to 1. I could write a utility to do this a little bit better. This one is 3. This one is 4. This one is 5. So now I have all 5 sectors of this file. They're here. So I just assembled all of them into one file. And let's actually take a look at what this something.bin actually is, to see if it actually looks like it's a valid FLEX binary. And it is. It looks like it loads some code, because you see down here, transfer address is 200. So we have some code starting at 200. Looks like it's a... Then we have some other thing here and some other thing here. Not going to worry about those too much. So since this is a FLEX binary, it looks like we should be able to disassemble that. And also, again, I actually have source code for this sector, which I can compare to see if it looks like we have the same thing. So let's go into that. So on the left side of the screen, I have the original source code, which is a tiny bit easier to follow than the disassembly, and I have the disassembly on the right. And the reason why I did this was so that I could actually clearly see that the code that I extracted off of track 34 on the disk is actually the same as what's contained in the source code. It turns out that it actually is. So if we read what this says, the comment at the top of this file, it's going to be fairly similar to what we saw in the one before. What we saw before was actually the fake PUTBOOT.loader. This code is actually the real code for PUTBOOT.loader. So its comment is a little bit different. PUTLoader places a Radio Shack TRS-80 CC, and note that this was before the term CoCo was introduced, so they still are calling it a TRS-80 color computer. PUTLoader places a Radio Shack CoCo disk extended color basic directory on a FLEX disk. The file FLEX.basic is written, and the loader is placed on sector 1609. The disk may then be linked for booting FLEX. The disk must be a newly formatted and double density. PUTLoader messes with the FLEX file structure to auto start. The first sector of PUTLoader should not appear in the directory. Instead, a fake sector, which is linked to itself, but which changes the link field in the FCB to point to PUTLoader during get, should be accessed by the directory PUTLoader entry. The PUTLoader code should be on a track inaccessible to backup. So this is the situation that we just found. We just basically figured out that the fake sector loads this sector off of track 34, and track 34 is not part of the FLEX file system. So a normal FLEX utility would never see track 34. And now the story actually kind of makes a whole lot of sense. The disk on the color computer archive doesn't actually have the code for this PUTLoader program because it's not part of the FLEX file system. It's off on a track that's not part of the file system, and the people that did the restoration before didn't figure this out. So when I actually had my master disk and it actually had it, then I'm able to put all of these pieces together. Okay, so I'm not going to go into excruciating detail here, but if we follow the code for what PUTLoader is doing, it kind of makes sense. This here is some kind of a patch to FLEX. I'm not completely clear on what this part does. Doesn't really matter. So we get the drive number from the command line. Remember we ran PUTLoader 0. And we get the drive number. Make sure that it's actually correct. Then we get the system information record from the drive. Here we actually check the number of tracks on the disk to make sure it's more than 17. Then we get the system information record again. And we open the directory, get the system information record, and then we actually check to make sure that the disk is unused. We check to make sure it's double density. Double-sided is okay, but at least it must be double density. Then it looks like we start doing our RS-DOS stuff. So what they do is they rewrite the disk. So granule 32 is on track 16. So what they do is on track 15, the last sector of the track, they actually point it to the end of the granule. So the FLEX disk actually skips granule 32, which is 9 sectors. They do this by reading the last sector, track 16, sector 9, which should point to track 16, sector 10, and they write that to track 15, sector 18, so that you have a skip, we can actually check that this is actually the case on the freshly created disk that we made. Okay, and they do a very similar thing here to claim the RSDOS FAT and directory, except this time it's track 17 sector 2 and track 17 sector 3. Those are the two that are skipped. So that's what this part does. It actually writes the basic program, and we're writing that to track 16 sector 1, which is the beginning of granule 32. And then we write the binary portion of the loader, and that gets written to track 16 sector 9. That's the end of granule 32. And then we write the Radio Shack directory, and we write the Radio Shack file allocation table. And the last thing that they do here is they update the system information record. We remove 11 sectors from the FLEX part of the disk because that's what we stole from it to put the Radio Shack information. So this is clearly the code that actually installs the bootable portion of the disk. Okay, that's what this code does. So I do have a graphic which will make this a little bit more clear about what's going on. Alright, so where we left off before is we talked about the FLEX part of the disk. We talked about the system information record, we talked about the directory sectors, and we talked about the remainder of the disk. This is where we left off before. Now we just looked at the code that actually installs the bootloader on the disk. So what it actually installed is in granule 32, which is track 16, sectors 1 through 9. In the first sector, it installed the basic program. In the last sector, it actually installed our IPL, our initial program loader. So this is the first 9 sectors, which we took away from FLEX to install the bootloader. Then on track 17, we need a directory and a FAT. So that's sectors 2 and 3 of track 17. So we also took those away from FLEX, and we installed a disk extended color basic file allocation table and a disk extended color basic directory. All of those got installed on the disk. And they were also removed from FLEX. So putting the whole thing together, we have the FLEX system information, which is on track 0. We have the disk extended color basic system information, which is on track 17, and those two sectors are not visible to FLEX. And then we have granule 32, and granule 32 is also not visible to FLEX, and we have the basic program and the initial program loader. So this is the structure and how the ColorFlex boot disk is actually put together. And we actually saw the actual disk, and we actually saw the actual code. We actually saw everything and figured out how this thing works and why the disks that were on the Color Computer Archive were not masters and why my disk is a master. Okay, I'm going to show a little bit more just to sort of put this all together. We should see the newly created boot disk to actually confirm what I'm showing in these slides is actually there. So let's go ahead and do that. Alright, so I'm going to run my disk tool again, but this time I am going to run test.dmk. So let's just quickly confirm the FLEX part of it. So system information records, this is the test disk. Note that it has 35 tracks this time, not 34. Right, we created it on July 11th of year 123. Cool, right? Okay, and if we look at the directory, there's only one file on there. We just copied flex.sys. Flex.sys starts at 001. So this is the flex portion of the disk. Just so this is the first sector of flex.sys, 101, or track 1, sector 1, and it goes to track 1, sector 2, etc. Right? We're not going to look at the whole thing here. So let's confirm the disk extended color basic part of this. So we said on 1702, there's a file allocation table. And this looks like a file allocation table. And so 1 byte is for each granule. So here is granule 32. And it says that this granule is in use, basically. And then here is the disk extended color basic directory. So when we put that disk in the machine, we actually see the flex.basic. And it says here that in this granule, EE bytes are being used in this granule. Great. So granule 32 starts at check 16 sector 1. Here's our basic program. And it's a little hard to see the basic program here. I'll go back to the emulator so that we can see that a little more clearly. And then it also said at 1609, it wrote our program bootloader. And yes, it did. Great. So I actually confirmed what we saw in the code, looking at the boot disk that we created, and confirmed that it's all here. Okay, one more thing. Go back to the emulator. And we're currently running Flex, but I'm just going to go ahead and restart this. We do a directory, and there's our flex.basic. So this is the program that we were just looking at. We already know that the code which actually boots up Flex is contained on drive 0, track 16, sector 9. That gets read into a variable, and all that this does is it gets the address of the variable, and this is actually a jump instruction. This is actually a pointer to the variable. And we just exec it, and the binary code reads in Flex, and it actually performs the boot that we've seen many, many times. So this actually loads in flex.sys from the disk, and then it jumps in to execute it. So we have seen beginning to end the entire thing, the entire story. And now you know in excruciating detail why the disks that were on the Color Computer Archive were not master disks, and how that sort of threw me astray, because I didn't try to use PUTBOOT.Loader on the master disk that I had. I just sort of assumed it was broken. I had seen the extra code on the disk. I was really confused in between whether it was 34 tracks and 35 tracks. It turns out I saw some data there, but I didn't quite know what it was. So I just said, fine, it's a 35 track disk. There's some data on there, but I didn't investigate. So finally, I go to make this video explaining that this is not a master disk. And then guess what? I found out that I was tricked. That the physical disk that I have actually is a master, and you can use this disk, which I've already published. I've published the disk images for this disk. You can use this disk to create new ones. I proved it. We looked at the code. All right. I think that's enough for this episode. I hope you guys enjoyed this. This episode is a little bit long-winded, but I felt like I needed to go into all of the nitty-gritty details, so yeah. I was duped. I actually had a master disk. Brian Weasler, you're off the hook now, because I have the holy grail of a Flex Master. However, if you find a different version of Flex Master, 502, 503, 504, 501, it would be very good to archive those too, but at least this saga is over. Alright guys, I think that's enough for this episode. Bye for now.